All right, so the first part is just expressing complex numbers in polar form. So what we mean by polar form is that you have a magnitude and an angle, and you have to be super careful with the angle that you get the right quadrant if you are not using the complex number features of your calculator, and you'll see what I mean in a minute. So first of all, if you have something in rectangular form, then that's of the form a plus jb, and the magnitude is the square root of a squared plus b squared. And the angle,
Hey, Rebecca, can you share your screen, please?
am I not sharing? Thank you.
Yeah.
Uh, right, I stopped sharing. Yeah, like I said, I don't see the chat until someone has told alerted me out loud, and then I'll see the chat. So you're welcome to put stuff in chat, and I will try to keep an eye on it, but likely not going to see it. Okay, so but thank you for those of you who spoke up. Thank you. Okay, so when you have a complex number in rectangular form, that means you have it in a plus jb. So it looks like a plus jb, and the magnitude is the square root of a squared plus b squared, and the angle is the inverse tangent of b over a, and then maybe plus or minus 180 degrees. Now, why would it be plus or minus 180 degrees? I'll explain that with this very first problem. So first of all, when you have a complex number and you look at where it is, you would graph it by saying the horizontal axis is the real axis and the vertical axis is the imaginary axis. So if I have a number like minus 6 minus j4, that has a equals negative 6, b equals negative 4. So it's negative 6 on the real axis and negative 4 on the imaginary axis. It's right there, and usually write it as a vector. So that is the imaginary number negative 6 minus j4. So if I want to write it in polar form, I need to get the length of this vector, and I need to get its angle, and its angle from the positive x-axis. And so the magnitude is going to be, when I square them, they'll be positive, so I'm not going to worry about putting the negative sign here. 6 squared plus 4 squared is square root of 36 plus 16, which is the square root 12, carry the 1, 52, which is, let me get what that is. 7.21. And then if I take the inverse tangent of b over a, so negative 4 over negative 6, so the inverse tangent, and on this calculator I just have to press the tangent button twice, negative 4 divided by negative 6, and it gives me 33.7 degrees. So 33.7 degrees. But you can see that this complex number is not 33.7 degrees from the positive x-axis. The reason why is the calculator is only going to give you values in the first and second quadrant. And so you have to know where your imaginary number is. And if your number is in the third quadrant, then you will add 180 degrees to the value from the calculator. I'm sorry, I lied. You're not. You're gonna subtract. And I don't know why I was saying. Okay, hold on. Yeah, I did. I'm really tired, and so I made a mistake. Usually in math, we measure angles from the positive x-axis. That is actually not what we do in circuits. What we do in circuits is all our angles have to be, but just by agreement, we have all of our angles between plus or minus 180 degrees. And so what we actually want to do, if our number is in the third quadrant, we actually want to subtract 180 for the value from the calculator. And so our angles should go from 0 to a negative 180 and 0 to a positive 180. And so I want to take 33.7, which is right here, and subtract 180 degrees from it. So 33.7 minus 180. And that gets me negative 146. So negative 146. And so my answer to this problem is 7.21 angle negative 146 degrees. Okay, questions on that? All right. J2. Now remember that this is the real axis and this is the imaginary axis. So if we have a number like J2, that is just on the imaginary axis. It's up 2 on the imaginary axis. So I don't have to do any work for this one. I know exactly where it is and how long it is. This is 2 angle 90 degrees, because that's where it is. And I'm going to do just one more of these. You can try the others on your own and ask me if you get them right. You can send them to me and I'll tell you if you get them right. So minus 1 plus j to the 1/2. So it is easy to take the square root of numbers if they are in polar format. It's a little bit harder to do. It's much harder to do if they are in if they're in a rectangular format. So what I want to do is I want to write minus 1 plus j in polar format and then take the square root. And I'm going to do this by kind of thinking about it. So minus 1 is this way on the horizontal axis, plus j is up 1 on the imaginary axis. So that's right there. And this is going to have magnitude, the square root of 1 squared plus 1 squared, or the square root of 2. That'll be its magnitude. And because these are the same length, this little part here is a 45-degree angle. So I know my angle is 135 degrees. And so this is 1 square root of 2, 1.41. So this is 1.41 angle 135 degrees. Now I need to take the square root of that. And to take the square root of something that is in polar form, I'm going to take the square root of the magnitude part, and I'll divide the angle by 2. So this will be 1.189 angle 67.5. Now just to see if we got that right, let's use our calculator. So we got, if I take if I take 1.189 and then go to complex angle 67.5, and I put that in, and then I square it, do I get back what I started with, which was -1 plus j? Negative 0.999, that's pretty much -1 plus 0.999 I. So yes, that did in fact work. Okay, so any questions on that before I go on to the next thing?
You just got 135 from doing the tangent inverse.
No, I could have gotten 135. No. So I did it by just thinking about it. I knew that, but I'll show you how to do it with tangent inverse because it would not give me the right answer. So I guess I should show you that. So I knew that since this was 1 and 1, that this was a 45-degree angle. And so this is 90 and this is 45, and 90 plus 45 is 135 degrees. So I just did it like that. But if I did inverse tangent of 1 over -1, let's see what happens. I would get inverse tangent of 1 divided by -1, and it gives me -45 degrees. And that's not what I want because -45 degrees is down here. And so if your number, if your complex number is in the second quadrant, you will add 180 degrees to the calculator answer. So you would take the -45 that it gave you plus 180, and that gives you 135 degrees. And so if it's in the third quadrant, you subtract 180. If it's in the second quadrant, you add 180. And if it's in the first or fourth, you'll be fine. It has the right answer. Okay. Other questions? All right. So if I have time, I'll try to come back and do the other two, but I don't think that's the most important thing to do right now. So let's look at taking something that's in some other form and putting it in rectangular form, and I'm just going to do a couple of these. So the first one, we have the square root of 3 e to the minus j 3 pi over 4. Now, when you write it like that, instead of square root of 3 angle, this would be 135 degrees, this number is in radians. And so if you want to figure out what it is in degrees, you don't need to, you can use radians, but if you want change it to degrees, radians times 180 over pi equals degrees. So when I write it with degrees, I use the angle. When I write it in radians, I put a to the minus j. Oh wait, this was minus 3 pi over 4. Hold on, so minus 3 pi over 4, that's going to be minus 135 degrees. So a to the j, e to the j theta, you use radians, and when you use the angle, you use degrees. But we want it in rectangular form, and so how do you go from polar form to rectangular form? Well, it's pretty easy. You're going to have that a equals r cosine theta, and b equals r sine theta. And it doesn't matter if you're in radians or degrees, just make sure your calculator is set right. So this would be the square root of 3 cosine negative 135 degrees, and this would be square root of 3 sine negative 135 degrees. So that's negative 1.22 is A, and then B is the square root of 3 times the sine of negative 135 degrees, which is also negative 1.22. So this is minus 1.22 minus j 1.22. Oh, by the way, when you write something as a phasor, you never have a negative magnitude. So let's say I had something that looked like negative 5 angle 90 degrees. Okay, or let me make this negative 5 angle 75 degrees. That's what I ended up with by doing some sort of calculation. Then this is not a good format. You need to always have positive. And so if you want to make this number positive, you'll either add or subtract 180 degrees from this angle. And the way you figure out which to do is you need to keep your answer between negative 180 and positive 180. So for this one, I would have to subtract 180 degrees, because if I added 180 degrees, it would be too big. So negative 105 degrees. That was just an aside. Okay, I'm going to do this one next. Minus j to the minus 4. Before I do that, I'm going to remind everybody that if I have 5 over j, that's the same as negative 5j. 1 over j is the same as negative j, and I will show you why. 1 over j, if I multiply that by j over j, I get j over j squared. J squared is negative 1, that's its definition, and j divided by negative 1 is negative j. So what is negative j to the negative 4th? That is negative 1 over j to the 4th, which is negative 1 over j squared times j squared. J squared is defined to be -1. That's what j is. So this is -1 over -1 times -1, or -1 over 1, which is -1, and that's my answer, and that is in rectangular form. And then I think I'm going to move on to some other problems. If you wanted to do something like this one, probably best to put it in polar first and then raise it to a power. So if I have A angle B raised to some power C, that is the same as A raised to the C angle B times C. Okay, so I'll move on now to determine the instantaneous time functions. So here I'm given some information and I need to write this as a sine or cosine, as a function of a sine or cosine. So for the first one, I have a current, and I have 6e j to the 60 degrees, so they're making a liar out of me by putting degrees in there with an e, which you can do, but you would definitely have to have the degree symbol, at a equals 60 hertz. Okay, f equals 60 hertz. So you need to remember that omega is 2 pi f. Omega is the angular frequency, and f is the frequency in hertz. And you'll need to have omega in order to write our function. And so this tells us that omega is 60 times 2 pi, or 120 pi, and I'm just going to leave it like that. And the 6 is our magnitude, so I1 equals 6, and we use cosines, so cosine 120 pi t, and then our phase is plus 60 degrees. Okay, so now let's do the next one. We have I2 equals minus 2e to the minus j 30 degrees at f equals 1 kilohertz. So we need to get omega, so omega will be 2 pi times 1,000, or 2,000 pi. And what's the problem right here with the way our current is written?
There's a negative in front.
Right, and how do you think I'm going to change that?
Subtract 180.
Yeah, I will subtract 180. Or will I add 180?
Wait, sorry,
add
I meant add 180.
Yeah, I'm going to add 180. So that'll give me aj to the 150 degrees. And when I do that, that becomes positive. So this means that this is I2 equals my magnitude, which is 2, cosine, and my angular frequency, 2,000 pi, and then t, and then plus 150 degrees. And I think, yeah, at this point I'm going to move on to some actual circuits problems, unless anyone has a question. All right, so this one is has more math in it than you would probably be required to do on the test, but you never know. So you want you want to know how to do it. So the question is asking, at what angular frequency is the current in phase with the source voltage? And then it says, what is the angular frequency? And I'm sorry, what is the resonant frequency? And probably not going to work this one all the way out because there's just too much math. But we will work it part of the way out. Okay. So how do I find where the resonant frequency is? Ricky, is there is there something funny? I mean, I'm serious. Is there so is there something about the resonant frequency that's humorous?
So sorry, something was just happening in the other room.
Oh, okay. I was hoping that we had something funny going on with the circuits, because that would be fun. Okay, so the way you find the resonant frequency is if you had an RLC circuit that was already set up nice, you could use a formula to find it, but really what we're looking for is the resonant frequency is the frequency that makes the imaginary part of the impedance equal to 0. So we don't have a voltage here yet. And I mean, we're not given a voltage, so we don't have a frequency. We're being asked something about the frequency. Now, this is currently not in the phasor domain. I could add my capacitors first and then cast it to the phasor domain, but they're a lot, well, no, they're a lot easier to add when we put them in the phasor domain, so we'll go ahead and do that first. So remember, capacitors are minus j over omega c, and inductors are j omega L, and resistors are just R. They're just whatever they are. And then everything is in ohms, and they all add like resistors. So the 108.33 times 10 to the negative 6 farads, so this is this first capacitor there. It is C1, and so in the phasor domain that would be minus j over omega times 108.33 times 10 to the minus 6. So then what we want to do, so that we makes it a little easier to work with, is let's figure out what 1 over 108.33 is, and it's 0.00923. Over omega. So that's the first one. Our inductor is j omega L, so that's j times omega times 0.2, so that's just j 0.2 omega, nothing else to do there. And then I have 2 millifarad capacitors, I'll call those C2 and C3. And that will be minus j over omega times 0.0002. And then if I do 1 divided by 0.0002, I get 5,000. So this is minus j 5,000 over omega. And that's for each of those. Now, when I look at my circuit, I can see that these 3 components are in series. And once I've put them in the phasor domain, I can just add them up. And so I get minus j 5,000 over omega, minus j 5,000 over omega, and then the last one was a resistor, which was 50 ohms. So just add those together. I get minus j 10,000 over omega plus 50 ohms. It'll be easier to work with later if I combine these. So minus j 10,000 over omega plus 50 omega over omega, or minus j 10,000 plus 50 omega over omega. Okay,
Oh,
so
for C1, why didn't you divide by 10 to the negative 6?
because I forgot and you reminded me, and I am very appreciative. I forgot to divide by 10 to the negative 6, and I forgot to divide, I did my millifarads, so let me get that. So it should be, yeah, hold on. Nine, 2, 3, 1. If you see me make a mistake like that, please let me know, and the sooner the better, because nobody wants to sit here and watch me work a problem wrong all the way through and then have to go back and do it again.
Is
So,
it 0.9231 or just 9231?
9231, now that we've put the times 10 to the negative 6 zone. So now what we have, I'll write it neater. We have minus j 9231 over omega and we have j 0.2 omega, and then this one is minus j 10,000 plus 50 omega over omega. Okay, now we have these 2 impedances in parallel, and then they together are in series with this one. So my total impedance is minus J9231 over omega plus, and then this will be product over sum, so plus J.2 omega times minus J 10,000 plus 50 omega over omega over J.2 omega plus minus J 10,000 plus 50 omega over omega. So this is minus J9231 over omega plus, now these omegas will cancel, and I want to get this, well, let me just go ahead, I won't do too many steps at once. So J.2 minus J 10,000 plus 50 omega over J.2 omega plus minus J 10,000 plus 50 omega over omega. I can distribute that 0.2j through on the numerator, so minus J9231 over omega plus, so j times j is -1, so j times minus j is +1, so then I just have 0.2 times 10,000, which is 2,000, plus 0.2 times 50, so plus J 10 omega over J.2 omega plus minus J 10,000 plus 50 omega over omega. Now, I don't like this complex fraction over here, so I'm going to multiply by omega over omega, and that gets me minus J9231 over omega plus 2,000 omega plus J10 omega squared over J.2 omega squared minus J 10,000 plus 50 omega. Okay, so now minus J9231 over omega plus 2,000 omega plus J10 omega squared over, and then in my denominator I want to put my real part together, that's 50 omega plus, and then my imaginary part is 0.2 omega squared minus 10,000 J. The reason I did that is because in order to, I need to get, my whole point is I need to get the omega that makes the imaginary part equal to 0. In order to do that, I need to get the denominators to not have any imaginary parts in them. We already don't have an imaginary part in the denominator for this first one, minus J9231 over omega. And then the way to get rid of the imaginary part in the denominator is to multiply by the conjugate.
I'm just wondering, like back in the calculations, did you put in the millifarads for the capacitor
I did.
and
Thanks
times it
for
by 10?
asking. I was afraid I didn't, but that's because I did because from the very start, I made it .00. Didn't I? Yeah, I think. Did I not? Let's see. Where are they? Yeah, I did it right here. .0002.
Just make sure.
Yeah, but thanks for checking. Yeah, I did. And then the inductor was .2 without any prefix. Okay, so I was multiplying by the conjugate. So then this is 50 omega minus 0.2 omega squared minus 10,000 J. Now, because my problem is just asking me for the resonant frequency, I don't actually care what my number is. I'm looking for the omega that makes the imaginary part equal to 0. And so to get the omega that makes the imaginary part equal to 0, I just need to make the imaginary part equal to 0. When I multiply by the conjugate, this denominator is going to be real. And a real part is not going to make the the real part is not going to make you can't the real part is not important in making the imaginary part equal to 0, so I don't really care what it is. So this is minus J9231 over omega plus 2000 omega plus J10 omega squared times 50 omega minus 0.2 omega squared minus 10,000 J over, and then what the denominator is when you multiply by the conjugate, it gets us 50 omega squared plus 0.2 omega squared minus 10,000 squared. Okay, so what I'm going to do with this problem is stop here because I'm going to tell you how you would go about solving it, but he's not going to give you one with this much math on it on the test. But I wanted to tell you the steps for going about doing it, because what you would do at this point is you would get a common denominator. And once you have a common denominator, I think I have extra syllables in there. Denominator. And you have one fraction, so you have one fraction. Then all you do is you take the imaginary part of the numerator and set equal to 0. You can ignore the denominator and you can ignore the real part of the numerator. You just take the imaginary part of the numerator and set it equal to 0. So you look at the parts that would be imaginary, you take them out and you set them equal to 0, and you find out what the omega would be. But he's not going to give you one that is this hard. Okay, so, but I did want to illustrate the concept. Yeah. All right, so now let's go on and do a circuit. Any questions before I go on from here? All right. So now we want to find the magnitude and phase shift, that just means the polar form, of the voltage V0 in the circuit below, given that our voltage source is 10 cosine omega t, the resistances are 220 ohm, 2.2 kilo ohm, 1 kilo ohm. We've got a capacitor that's 0.47 microfarads, another capacitor that's 1.5 microfarads, and an inductor. And we have the frequency is 2.5 kilohertz, and that means the angular frequency is 2 pi times the frequency. So what I would like everyone to do, including me, is let's get these values in the phasor domain, and then I'm not going to do it out loud. As a matter of fact, I'm not even going to share my screen. We're all just going to do these and then see if we have the right answers, and then we'll move on from there. So I'm going to stop sharing my screen, and I want everybody to convert these values. So you're going to use Z, the impedance for the capacitor is minus J over omega C, and Z for the inductor is J omega L. Z for the resistor is just the resistance, and you'll need to find omega. Omega will be 2 pi times 2.5 kilo, so 2.5 times 1,000 will be omega. So I'm going to stop sharing my screen, and I'd like everybody to work this, and then we'll get back together and see how many mistakes I made.
For the question, for problem 1, how do you do the first part of that question? Finding the angular frequency when the current is in phase with the source voltage?
It's the same answer.
Oh, okay. Thank you.
Yeah. Yes. Because if the imaginary part of the impedance is 0, I'll share my screen. Where's my Zoom? Thank you so much for the people who are telling me why they were leaving. That just makes me very happy. Okay, so we know that V equals I times Z. Now, if the imaginary part of the impedance is 0, then that's going to make Z have angle 0. So this is going to be V equals I if we find the resonant frequency. This is not for this problem, by the way. This is for the problem before. The question is, why does the resonant frequency mean that the voltage and the currents have the same phase? Because this will then be angle 0. So if that's angle 0, that means the voltage and the current have to have the same phase angle. Okay, now we're going to find our values. Okay, let's see how many of them I got wrong. Anybody see any that I got wrong?
I got the same answer as those.
Wow, it's like the first time in my life. All right.
What was the first? What was C1's value?
For
Like
C,
the non-phasor value, the initial value.
it was 0.47 microfarads. So for C1, we had minus J over omega C. So it's minus J over omega. I got to be 15707 times C1 0.47 times 10 to the negative 6. So minus 1 over 15707 EE negative 6. So that is not the same. Oh, I forgot the. Yeah, that one's wrong. So minus 1 over 15707 times 0.47 EE negative 6. Negative 135.45.
Yeah, I think I just typed it in the calculator wrong. I got everything else the same, and then when I redid it, I got negative 135.
Okay, good. All right. Okay. So now the problem is asking us to find the voltage across this resistor right there. So if we knew the current right there, then we could find the voltage across the resistor. And so there are, always a million different ways to go about solving a circuit. Um, and uh, I always like nodal analysis, but we could also do mesh. Um, but I think the first thing I would do with this one is to combine those two middle that are in parallel. And so the ones that are in parallel, that'll be minus J 135.45 times 2200 over minus J 135.45 plus 2200. And I'm now no longer concerned about not using my calculator, so I will do and I get 0.308 minus J 134.9. .308 minus J. What was it? Anyone?
134.
134 point something. I don't know why it's not letting me go over to the left. 134.9. 134.9. Okay, so the problem is that there's just no fun way to go about doing it. And let's see, over here we can combine all of these that are in series. So I can put together my 471 minus 42.44, and I get 428.56. It's not looking too bad. So let's just and I'm looking for, if I know the current going through, well, if I know the current going, if I know the current going through this branch, I just multiply it by 1,000 to get the voltage across that resistor. Yeah, so I think what I would do, actually, I'm just going to, actually I can get the voltage directly. So if I make this V and make this ground, then I can set up one nodal equation, and I can say V minus 10 over 220 plus V over 8.308 J 134.9 plus V over 1000 plus J 428.56 equals 0. And that V is not the V I want, it's the V from here to here. So it's not just the voltage across the 1000 ohm resistor, but it's well on my way to that. So this is the same as V over 220 plus V over 8.308 minus J 139.9 plus V over 1000 plus J 428.56 equals, and then I'll bring the 10 over 220 over to this side. So I just factored the V out, and now, because my calculator is awesome, I can just add these together. So 1 over 220 plus 1 over 8.308 minus J 139.9 plus 1 over 1000 plus J 428.56. And I get 0.0058 plus 0.00676 J. And then I can get V equals 0.04545 over 0.00581 plus 0.00676 J. And I'm going to change that to polar. And I get 5.09 angle negative 49. .3 degrees. Okay, so that is the voltage right here. And I originally was talking about finding the current and multiplying by 1000, But now I think voltage division would be a better way to go, because I know the voltage right here is 5.09 angle negative 49.3, and then I've got these two together made J 428.56. And then I've got the resistor is 1000, and I've got ground right here. And so I can do voltage division. And so voltage division tells me that the voltage across the 1000 ohm resistor is going to be my total voltage, 5.09 angle negative 49.3, times 1000 over the sum of the impedances, 1000 plus J 428.56. So I have the angle right, I have this number right there is already in my calculator, so I can just take that times and then fraction 1000 over 1000 plus J 428.56. Enter. I'll change that to polar. And I get 4.69 angle negative 72.5. Volts, and that would be my answer. Okay, questions on that one? I'm gonna have to stop for tonight, seeing as how it's 9 o'clock, but I will go ahead and record the last one, which is finding a Thevenin equivalent circuit. I'll record that and post it. Do y'all have anything else that you want me to do to have available for y'all tomorrow as you study for this test?
I just have one question.
Sure.
Um, he gave us his acronym, Eli the Iceman. Is there anything on there that we would have to use that for?
Um,
Like, like how does that pertain to us? Because I haven't
okay,
used it yet.
so he does like Eli the Iceman. Um, so let me so if the imaginary part of the impedance is negative, it is capacitive. If the imaginary part of the impedance is positive, it is inductive. And give me a second. There are some things I can never remember right. And inductive loads, the current lags the voltage. And for capacitive, current leads voltage. And I don't actually know. I never. What does anyone? Can anyone explain Eli the Iceman?
Yeah, so the E would be voltage. So
Uh huh.
if it's inductive, then it would be voltage leads current.
Yep.
And then if it's capacitive, it would be the current is leading the voltage because the I comes first.
Okay. So E is like EMF for voltage. Yeah. I can't remember this. So E is for voltage. L is because it's inductive, and that's our symbol for inductance. Um, and for inductive, uh, current lags the voltage. So the voltage leads the current because voltage comes in front of it. And then for ice, it's the other way around. Okay, so okay, I finally get Eli the Iceman. Finally get it. So ELI. So voltage, current, and inductive. So voltage, the current lags the voltage. Yeah. Okay. So anyway, so anything you need to know about, you do need to know these things. I don't know what else you need to know about it at this point. Any other questions? All right, well, if you think of something, I will record this last problem. Oh, and did y'all see that I put up a playlist of things that I've done in the past?
Yes, thank you.
You're welcome. I never go back and look at them, so I don't know if they're any good or not. But you should find a lot more examples there, um, because there's only so much that I can do in a limited amount of time. We did not practice as much of the circuit techniques as I would have liked, so I'm probably going to try to do something like that with that tomorrow. All right, so if you have any questions, do feel free to email me, and good luck. I hope y'all do great.
Thank you.
You're
Thank you.
welcome. You're welcome.
Thank you.